Hi and welcome to another instalment of Mantis Hacks. If you've been following the channel, you will know I'm building a gripper head for the Mantis robot. If you don't know what the Mantis robot is, check out the links. And in the last episode we were getting some Arduino code written to talk to the feedback encoders, and here is one of them right here. So that's all working now, and we've got feedback running, which will eventually be installed at this point here on the gripper. So the next thing to do is basically add the control side of it, so I can talk to the valves, the special hydraulic valves that will close the loop on the gripper. Now to do that, I've got to add a few things to the Arduino. One of the first things I'm going to do is, I've already installed it on the board there, but it's a little tiny device, and it's a little digital to analog converter. It's based on the MCP4725 chip, which is a microchip device. And the reason why I'm using a dedicated DAC for this rather than using analog write on the Arduino is because the analog write won't run fast enough for me to update the servo valve. So basically you're effectively converting a pulse width modulated signal to an analog signal via an RC network if you're using the analog write on an Arduino. And I just can't get the frequency I need to run at, so I'm going to use a dedicated DAC for that, which will run nice and fast. And these are very cheap and very easy to rig up. They basically sit on a little I2C bus. This particular device has two addresses, so you can have two of these on the same bus with different addresses. So the output from that is 0 to 5 volts. So that's the first step. The first thing I'm going to do before I close the loop completely is just rig the valve up so that I can control it in open loop mode. So effectively I'm going to put I've put this little lead on the Arduino here, which is hooked up to my analog input 0, and I'll put a potentiometer on that so I can read the potentiometer and effectively send out a drive signal to the valve according to the position of the potentiometer. And that will literally just shuttle the valve in either direction, so it'll be fully open loop, but at least it's the first place to start, so I can see that the valve is actually working and doing what it should do. So I've already installed the little one of my little MCP DAC devices in here. So the next thing to do is have a look at writing some code and getting an output from the DAC. Okay, let's take a quick look at the Arduino now. So I've got my DAC breakout board plugged in over here, and that is connected to VCC and also the I2C pins on the Arduino. The output of the DAC board is coming back into the Arduino into one of the analog input pins, and I've also got my potentiometer plugged in into one of those analog input pins. So the DAC breakout board I'm using is very similar to the Adafruit version. The difference being the Adafruit has a pin for the address bit on the device, whereas this little board that I'm using just has this little solder pad area, so you can short out to either ground or VCC to set the address. Right, so let's take a look at the sketch. So I'm using the Adafruit library, and I've started with their triangle wave example, which basically outputs a triangle wave to the DAC output. So here's the top of the sketch. I include the library, set a couple of pins up here. This is my potentiometer input, and this is the DAC output fed back into the Arduino. My LED pin, here's the DAC object, a couple of variables, and then we've got our our setup routine, and we start the DAC up with address 62, and that is basically the default address of an A1 device. As I said, there's several devices you can have for different addresses, and I've got my address pin grounded, so that makes it address 62. And now we go down to the loop, and basically this is their triangle wave generator, so it counts from 0 to 4095 and then back down to 0 again. And all I've done is I've added some flashing the LED pin here just so I can see it's running. There's the DAC set voltage routine, and then I'm reading the DAC output on the analog input of the Arduino and also the pot input, and displaying that data using these functions down here. So nothing very special there. And obviously this is a 12-bit DAC, and that's why we're counting to 4095 to get the full output swing. So that's already running on the Arduino. Let's have a look at the output of that using the serial plotter. There we go. So the blue triangle wave is the output of the DAC, and the orange output is the potentiometer. There we go. Move the potentiometer around. So that's working pretty well. The next thing I need to do is integrate that code into the gripper code that I started before. So that's already got the header in here, but I need to add in the code to read the potentiometer and then output that value to the DAC. And also I then need to find a way of connecting the DAC to the valve. And that needs a little bit of another piece of electronics in between, because the valve is a current loop input and the DAC is a 0 to 5 volt output. So that's what I'll be looking at doing next. Okay, so now we need to convert that DAC output of 0 to 5 volts into the current loop type signal, which is 4 to 20 milliamps, which is what this valve currently uses. So the 4 to 20 milliamp signal basically is very good because it's good for noise immunity, and effectively 12 milliamps is where the valve is in the middle of its travel, 20 milliamps it's at one end of its travel, and 4 milliamps it's at the other end of its travel. And the range from 0 to 4 milliamps is basically an invalid signal, and with this particular valve it will shuttle back into a fourth position, which is like all ports blocked as a safety feature. So what we're going to do is use an operational amplifier. I'm going to use the LM358, which is a single supply amplifier up to 32 volts. And this is the schematic that I've set up to convert that voltage to a current. So over here we have the Arduino, and this side is the valve. And basically the little OpAmp circuit is pretty simple. It takes the DAC output from the Arduino, which is 0 to 5 volts, into the non-inverting input of the amplifier, and effectively the circuit is configured so that the inverting input will try and match the non-inverting input. So if I'm supplying 5 volts here, the amplifier will give enough current flowing through the loop to give 5 volts here over R1, and 5 over 250 ohms is 20 milliamps. So that gives us our full range of 0 to 5 volts from 0 to 20 milliamps. Now the loop through here, obviously you need slightly higher rail voltages to be able to supply 5 volts here, and I've got another load within the amplifier here, a load resistance. I need a higher rail voltage on the amplifier to be able to supply this. So I'm running it currently at 24 volts. Just because the amplifier already has 24 volts power supply to it, so I'm stealing the same supply for that, or I will do eventually anyway. So quick calculation tells me that 24 over 20 milliamps minus the 250 ohms of R1 gives me a maximum load of 950 ohms in the amplifier, or whatever else it is I'm trying to drive. I think as it happens the amplifier has a load of about 100 or 200 ohms, so that's plenty of headroom to supply that load. So what I've rigged up at the moment on the Arduino here, let's take a little look. So I've got my operational amplifier in the separate breadboard here. I've got the V-in power supply and ground from the Arduino. I've actually put a 12 volt jack into here just to give me enough headroom on the amplifier to do some testing before I plug it into the valve. And then basically got the DAC output coming into the amplifier. Here's another ground there. We don't really need it, we've already got one here, but it's in there for good measure. And then what I've done is I've taken an output from the amplifier back to one of my analog inputs on the Arduino so that I can measure how much current there is flowing through the system and see that in real time. So the current flow measuring point, what I've done is, this is the point here, it's the inverting input to the amplifier, which I'm taking a point out of here and feeding back to one of the analog input pins on the Arduino. And so this point here should measure between 0 and 5 volts as I apply a DAC voltage here. And that will tell me how much current is flowing through the loop, because I can do my calculation using the resistor R1 to work that out.
and see it in real time. So let's take a look at the code. Okay, so here's the updated sketch. I've added in the Adafruit library for the DAC. I've added in some more definitions in my two analog input pins here, which is the potentiometer and the DAC feedback, so I can monitor the current flow. I have some more definitions defined down here, which is basically the voltage range of the DAC, the resistor R1, which we're looking at here, and then the analog input range and the DAC output range. The maximum microamps I'm using for calculations within the various parts down here, and that's basically works out at 20,000 microamps maximum output. Basically I'm using the loop neutral here at 12,000 microamps, so the loop neutral is where the valve sits in the middle, and then I've defined the swing range either side of that, so I don't want my potentiometer to straight away drive my valve from its midpoint to fully open or fully open in the other direction, because it's going to be a massive flow of oil and it's too much. So I just want to do a very small amount of movements to start with until I'm happy with the way it's working. And to do that, I've just set up this loop swing, so it's telling me that I can have 1,000 microamps either side of the loop neutral, and I'll see how that's these definitions are used in a minute. The loop tune there is currently set at 0, and that's just to tune the center point of the valve. So when it's supposed to be at 12,000 microamps, just to make sure it's sitting dead center, and also to add a little bit of offset to the valve, because when these valves are underlapped, and without going into too much explanation of what that is, when you've got a cylinder which has a different bore to the annulus side, there's different surface areas, it will want to drift in one direction. Especially without a closed loop control. So I can also tune the loop slightly so that the center point will stop that drift from happening. So let's just go down in the setup. I've added the DAC there just to start the DAC routines going, and in the main loop I've added, so here's my encoder stuff, we did that in the last episode, and then we've got read the pot here, so there's my pot input, and that's just using this analog read functions down here, and then write to the DAC, and then read the DAC output, so I can display data on the screen to show me how many milliamps are currently flowing. The display data down here, I'll go into what I'm doing here. There's a couple of floating point math functions down here just to convert the data so that I can display it in milliamps, so it's nice and easy to read. So let's just have a look at the update DAC output routine, and that's over here. And what I've got here is basically an interpolation routine, so it's linear interpolation, and the way that works is it takes works up to 16-bit integer resolution, and it takes a value and scales it between a low point and a high point to an output of a low point and a high point. So you have x somewhere between in low and in high, and gives you a value out between out low and out high. So basically just a scaling routine. And then I'm using that to scale the potentiometer input from its full range of 0 to 1023, and I'm scaling that to that 12,000 microamps less 1,000 and plus 1,000. So, and those are defined here. So there's the in low and the out, sorry, the out low and the out high. So what I get out of that routine should be the value of the DAC to send according to the scale that I've required. I also add the loop tune there, which is obviously set at 0 at the moment, so that has no effect. I then just clamp the output to make sure we're not going above or beyond the limits, so not above 20,000 or microamps or below 4,000 microamps, and then I write it to the DAC. Okay, so let's just start this off and see how it goes. Let's flip that back, start up the terminal. Okay, so what I've got here running at the moment, so I'm going to go down to my display analog data routine. So the first number you can see there is the voltage that I'm reading back at this point here. And then there's a little conversion here. So this is the loop return voltage, and that's basically just reading in from the analog input on the Arduino to give me the voltage. So it's currently saying, for example, 3 volts here. And then I'm converting that into milliamps by taking that return voltage multiplied by 1000 and divided by R1 resistance, which is 250 ohms. And I'm just printing those out to the serial monitor. So at 3 volts, see if I can pull that down. There we go, the potentiometer in the middle. We should have 12,000 microamps, 12 milliamps flowing, which should keep our valve in the center position. And then at one end of the potentiometer, we've got 13 milliamps, and at the other end of the potentiometer, we've got 11 milliamps. So that's working really nicely. So that's that loop swing range we set earlier on in the code. So I think now it's time to hook it up to the valve and see something moving.
Okay, so I have wired up my connector ready to plug into my valve, and this is a Hirschman type connector, and I've only used 4 pins on here, so there's power on the red and black leads and the current loops on the white and blue leads, and the power supplied by this 24 volt power supply back here. So basically on the current on the OpAmp on the next to the Arduino here, I've basically replaced the 100 ohms load that I had on the loop with the loop connectors, so that currently it's open circuit because it's not plugged into anything. And if I look on my screen, I can see that with my potentiometer in the middle, which should be about the 12 milliamp range, I've got 0 milliamps flowing, and that's because the loop is open. So I'm going to plug this into the valve now, and when I do that, hopefully should see, there we go. So I can see on the screen now that the Arduino's, the OpAmp is supplying about 12 milliamps to the valve, and if I wind the potentiometer up and down, I can see that current changing. So let's leave it in the middle, about 12 milliamps. The valve is still switched off at the moment, so I'm just going to turn that on now, and I can hear it winding. Now obviously it's not connected to anything yet, but I should be able to hear it if I wind it up and down. Yep, I can hear that changing, so I can hear the spool moving in the valve there. So that sounds like it's working. So really the next step is to install the valve onto the manifold block and try in open loop mode on the grippers. I was considering putting this valve on another station on the manifold, like so, but actually it'd be much faster if I just take off this manual valve here and replace it with the proportional valve and get it tested. Right, so I'm ready for this first open loop control mode test. So basically the potentiometer should be roughly in the mid position at the moment, so the valve should be in its kind of off state, let's say. The gripper has been plumbed up, so basically when I move the pot back and forwards it should open and close the gripper. That's the idea, so let's give it a go. Turn on the valve, get the pump going. And here we go. Great. Well, that's excellent. That's working really nicely. So I've got a really nice, smooth, proportional control in both directions. It's still only using about 1/8 of the travel of the valve because they're very high flow rate valves. So I trimmed that back using that the loop swing variable in the Arduino code. But that's working really nicely. So basically everything is in place now to close the loop up, because we've got our encoder running in the background here still, and that could be fitted here. I've then got to write the PID code to close up that loop using the encoder, and hopefully I'll get that done in the next instalment of Mantis Hacks. Hope you enjoyed it, and I'll see you again soon.